for question 6 on the fall 2019 exam, we're given this function, f of x is e to the x cosine x, just on the interval from 0 to 2 pi. And we're asked two things: find the intervals on which f is increasing and decreasing, and then find the open intervals on which it's concave up and concave down. So for increasing and decreasing, I'm going to be taking a look at the derivative. So this is going to be a product rule. So it's going to be the derivative of e to the x times cosine of x plus e to the x times the derivative of cosine of x. So that's just e to the x cosine x minus e to the x sine x. Derivative of cosine is negative sine, and I just bumped that negative to the front. Probably easiest to work with if I factor out that e to the x. So that's e to the x cosine x minus sine x in parentheses there. Okay, now that derivative is always defined. Okay. AD is my abbreviation for always defined. So I'm not going to have any critical numbers from the derivative being undefined. Any of my critical numbers will be from the derivative being 0. So if f prime of x is equal to 0, that means either e to the x is 0 or cosine of x minus sine of x is equal to 0. Well, that's just never going to happen. E to the x is never 0. This would mean that cosine of x is equal to sine of x. Okay. So I want to think, we're just working between 0 and 2 pi. That would correspond to going around once, rotating through the quadrants. And so I'm going to have a solution in quadrant 1 and a solution in quadrant 3, because those are the two quadrants where sine and cosine have the same sign. They can't be equal to each other if they don't have the same sign. They're both positive in quadrant 1. They're both negative in quadrant 3. So I'm going to have one value of x that's just an acute angle and one value of x that rotates a little bit past pi. And then I just want to see, well, what's my reference angle? Whatever angle I have here, that's going to be my reference angle here, and it's going to be the acute angle that has the same sine and cosine. Well, I ought to be able to recognize that's just going to be pi over 4. That makes this little reference angle right in here pi over 4, so that x is pi plus pi over 4, which would be 5 pi over 4. So I've got two critical numbers in this interval, pi over 4 and 5 pi over 4. Okay, so I'm going to keep up the formula for the derivative here, but just erase this work in finding those critical numbers. And I'm just going to draw a number line for f prime, making sure that I indicate I'm just working from 0 to 2 pi, because I'm going to be picking some test numbers here. So we had pi over 4 and 5 pi over 4. Obviously my number line here is not drawn to scale. I'm not super concerned about that. But I need to pick a test number in this interval. So I'm picking something that's smaller than pi over 4, but I can't pick something like negative 2 pi, because that's so far to the left of 0, there are going to be some critical numbers in between here and there. Okay. Now, what I can do, if I like, is I can actually pick 0 as my test number, because 0's there not because the derivative was 0 at that point, but simply because it was the end point of my interval. So I know that it's possible the derivative changes sign here. It doesn't change sign again until it hits the next critical number to the left of pi over 4, and that's going to be somewhere to the left of 0. So if I want, I can use 0 as my test number here. If I plug that in, the e to the x is always positive. Cosine of 0 is 1. Sine of 0 is 0. So this factor is positive. So my derivative is positive. Between pi over 4 and 5 pi over 4, I'm just going to plug in pi, because that's nice and simple. E to the x is always positive. Cosine of pi is negative 1. Sine of pi is 0. That's going to make that second factor negative, so that the derivative is negative. And between 5 pi over 4 and 2 pi, I'm just going to pick 3 pi over 2. Again, because 2 pi is there because it's an endpoint, not actually a critical number. If I wanted to, I could choose 2 pi as my test number. 3 pi over 2 is good enough. Positive. Cosine is going to be 0. Sine is going to be negative 1. 0 minus negative 1 is positive. So my function goes up and then down and then up. So I can say that f is going to be increasing from 0 to pi over 4, union from 5 pi over 4 to 2 pi. And remember, if we have a continuous function, and this is definitely continuous, then even though the derivative is not positive at these critical numbers, we include those finite numbers in our interval. Because the definition of increasing and decreasing isn't about what's happening at that one point. At that one point, the function is just being what it is. It's about comparing that point to other points. And if I compare the value at pi over 4 to the value anywhere else in this interval, which would be to the left of it, the value to the left is going to be lower because we're increasing. So that endpoint does get included. F is then decreasing from pi over 4 to 5 pi over 4. I include those endpoints. This does not mean I'm saying that f is increasing at pi over 4 and decreasing at pi over 4. Because again, the definition of increasing and decreasing is not about what's happening at an individual point. It's talking about what happens if you compare points in an interval. And if I compare points in this interval, the point on the left is lower. And if I compare points in this interval, the point on the left is higher. Okay, so that's our increasing and decreasing. Now I also wanted to get concave up and concave down. So for that, we're going to need the second derivative. I think I like this factored version of the first derivative because I can see I'm going to need to use the product rule again. But if I go with the non-factored version, I'd have to use the product rule twice. I'd prefer to just use it once. So I think since I've got that right here, this should give me enough room to work out f double prime. So f double prime, we'll use product rule again. That's going to be the derivative of e to the x times cosine x minus sine x plus e to the x times the derivative of cosine x minus sine x. So that's going to be e to the x times cosine x minus sine x plus e to the x times the derivative of cosine is going to be negative sine x minus the derivative of sine is just cosine of x. Once again, there's an e to the x in both terms, so I'm going to factor out that e to the x. And so it's times cosine x minus sine x minus sine x minus cosine x. Now the cosine x and the minus cosine x will cancel each other out. So I'm just going to get negative 2 e to the x sine x, because these combine to just give me negative 2 sine x. All right, so that's my second derivative. Let's just make a quick note that that's always defined. So we won't have any places where the second derivative changes sign because it's undefined. If it's going to change sign, it's only going to do that at places where it's equal to 0. So now I can draw a number line for f double prime. Again, just working on the interval from 0 to 2 pi. There's f double prime. Let's see the places where it could change. I want to see where negative 2 e to the x sine x is equal to 0. So either negative 2 e to the x is 0 or sine x is 0. That's never true because e to the x is never 0. Sine of x would be 0 at 0, pi, and 2 pi. So notice this time I'm not going to be able to plug in my endpoints as test numbers because now they're on the number line for two reasons. One, they were my given endpoints, but two, they're places where f double prime is 0 so that it could potentially change sign. Noticing that all the numbers I have here are quadrantal, rather than picking specific test numbers, I'm just going to notice that this is quadrants 1 and 2, and from pi to 2 pi would correspond to quadrants 3 and 4. So let's see. In quadrants 1 and 2, sine is positive, so that would be positive. E to the x is positive, but I'm multiplying by a negative 2. So my second derivative will be negative. In quadrants 3 and 4, sine is negative, so that's a negative times a positive times a negative. That's going to give me something positive. So we're concave down and then concave up. So we will be concave down from 0 to pi. Now I actually explicitly stated in the directions on this exam to give the open intervals where we were concave up or down. If I hadn't specified open, it would still be open. We don't include endpoints where the second derivative is 0, because the definition of concavity is that when we're concave down, if I draw the tangent line, it's below the curve. I'm sorry, if we're concave up, which is what I drew here, the tangent line is below the curve. Over here, where we're concave down, the tangent line is above the curve. Here's my point of inflection where we change. The tangent line crosses the curve. So at a point of inflection, the tangent line will cross the curve. Therefore, at that point, we don't satisfy the definition for concave up, tangent line below the curve, or concave down, tangent line above the curve. So we don't include finite endpoints for intervals of concavity, but we do if we have a continuous function for intervals of increase and decrease. Okay, and then we're concave up, of course, from pi to 2 pi.